Hello, welcome to this class of digital electronics. Today we shall learn about the sequential logic circuit. So the topic is here written sequential logic circuit. So let me see what are you able to see here. This is stop sharing. We will go and we are not there. This is what I wanted to show is this. Yeah, so this is the chapter number 5, which is synchronous sequential logic circuit, more specifically. Sequential logic circuit. So as you can see here, so far as definition of sequential logic is concerned, sequential logic circuit is a digital circuit in which output is the output. Output is a function of input as well as the past output, okay, or previous output. So in combination logic circuit, output is a function of only input conditions. This is a combination logic circuit. But in sequential logic circuit, there is a varying element through which some portion of the output is fed back to the input, and then output becomes the function of not only the input but also whatever past output was there. So this is the by definition what is meant by sequential logic circuit. So combination logic circuit we have already studied. Now we are moving towards the sequential logic circuit. In sequential logic circuit, there is a Waverly element. What is this Waverly element? A flip-flop is a Waverly element. So here definition is also written. Let us see. A sequential circuit is specified by a time sequence of inputs, outputs, and the internal states. What are these internal states? These internal states refer these states of this Waverly elements. So output is a function of input as well as the time sequence, because there is, since we are talking about sequential, so it is a sequential a time sequence of inputs, outputs, and internal states. So in contrast, the output of a combination logic depends only on the present values of the input. So there are two types here of this sequential logic circuit. One is called a synchronous sequential circuit, is a system whose behavior can be defined from the knowledge of its signal at discrete instant of time. Is the synchronous. The behavior of an asynchronous sequential logic circuit depends upon the input signal at any instant of time and the order in which the input changes. So this is the two things. First is the input signal at any start of time and the order in which the input changes. We will see later on with example the sequential and synchronous and asynchronous logic circuit. So let us begin with this here. More specifically, you can see the memory element is now implemented with the help of flip-flop. So here this is a clock, computational circuits, input, and this is the final output. So this is your timing diagram of the clock bus, which is here. Sorry, this is the feedback. This is the clock bus here, which is given to the input of flip-flop. So flip-flop has two things. One is the output of, say, combination logic circuit, or any input to any appropriate input to the flip-flop, and second one is the clock. So, okay, let us move towards this latches. Latches is basically a bistable device, okay, which generally we do not have block. So storage element that operates with signal level rather than the signal transitions are referred to as the latches. They works on the signal level instead of what is sequence of transition. Those controlled by the clock transitions are flip-flop. Okay, the states of the device which is controlled by a clock, clock called flip-flop. Otherwise, it is a latch. Both are abbreviated. So let us see this SR latch. I will draw this diagram and we will let you know. Let me use this jamboard. I will show you where this jamboard. It is visible. I think jamboard is visible. Yeah, jamboard must be visible. So sequential logic circuit, we start with SR latch. SR latch. Since most of the time we implement circuit with the help of universal gate, that is called NAND gate, NAND gate. So I will realize with the help of NAND gate. This SR latch with the help of NAND gate. So SR latch with the help of NAND gate looks like this. This is a NAND gate. Here is another NAND gate. So what input is here? Another input is here. This is called S. This is called R. This is called Q. And this is called bar. So output of this first NAND gate is given to the input of second NAND gate. Similarly, the output of second NAND gate becomes the input of first NAND gate. So this is the cross-coupled connection of two NAND gates. Okay, so this is your SR. S reset, R means reset. Set, reset, latch. Let us try to understand its function. So here we write input, here we write output. So we have two inputs. These are the inputs, and these are the outputs. So input we have S and I, and output we have Q and Q bar. Okay. So let us take different values, possible values. Suppose S is 1 and R is 0. This is 1 and this is 0. So what shall be the output? So in that gate, we have two input. Here also we have two inputs. So suppose this is the bit 1 or this is the bit 2. So as soon as this 1 is available here at the input of NAND gate number 1, we cannot predict what shall be the output. We have to look what is the output of input of second input of first NAND gate. Okay, this is the case regarding the first NAND gate. Now what about this one? In NAND gate number 2, we see R is 0 and this we do not know what it is because this depends on the output of first one. And first one output depends on the output of second one. So this is very puzzling situation. But here we shall able to resolve this issue and we tell how. In the input 0, the NAND gates waits logic 1. That we can tell with surety. How? Let us write here two table of NAND. A with Y. 0, 0 1 1 0 1. This I am writing the NAND gate. The NAND gate symbol is like this: A, B, and 1. So we know NAND gate is nothing but AND gate and then putting the NOT gate. This is the expected form of NAND gate. So 0 into 0, because this is AND and then taking its bar. So 0 into 0 will be 0. And complement of 0, this NOT gate will give output 1. Here 0 multiplied by 1 will give you 0, and 0 is available here, so output will be 1. Same case for this, 1 0 is 1. However, if it is 1 1, then output will be 1, because 1 multiplied by 1 will be 1. And this NAND gate, NOT gate makes this 1 logic to 0. So the output will be 0. Now just observe what we can infer, what we can infer from here. Inference. What is the inference? Inference is that this is 0, this is 0, and this is 0. Any 0 in the input makes the output 1. No need to look others. This is 0, this is 0, this is 0. This is what we can interpret here. Any 0, that is what I was trying to tell, that if any 0 is available in the input of that gate, makes the output logic 1. Suppose you had 10 input that gate there. 1, 2, 3, 4, 5, 6. So a lot of combinations are there. 1, 1, 1, 1. But only 1 0. Only 1 0 makes output logic 1. Okay. In order to make logic 0, all input should have 1. Then only it will be. This is the truth table, simple truth table. And from there we can tell that the output of second AND gate will be 0, and this is Q bar. So Q bar is 1. So obviously Q will be 0. So this is the first case of your latch, SR latch. Now I will remove this one. Okay, let me not remove. Okay, so that for reference purpose. Now take the case of, after that, if we have the input is 1 1. Okay, so I will take the input 1 1. One, 1. So both are 1 1. So we cannot tell with certainty what is the output. Why? Because we have to look other. What is the status? Like here, this is 1, this is 1. We have to look what is the status of others. If it is 1, then it will be 0. Or if it is 0, then it will be 1. So now we have to look what is the input, what is the status of input of this second one, here and here. So we know here earlier, since earlier it was 1 0, then output was 0 and 1. So this is here 0, this is 1. So this 0 is coming to here, and this is 1. So 0 1 makes output 1. And this 1 is coming here. 1 1 makes output 0. 1 1 makes output 0. So this will be 0, and this will be 1. So what is conclusion here? Conclusion is that there is no change. And here conclusion is that when S is 1, R is 0, so Q is 0, and R is, Q bar is 1. Now take the another scenario. Instead of 0 1 0, it is say 0 1. Okay. So there is no time sequence, that is why I am taking it this way arbitrarily. So S is equal to 0, R is equal to 1. So S is equal to 0, R is equal to 1. So output of first NAND gate will be what? Immediately we can tell, because any input 0 in the NAND gate means output 1. We can write here 1. And this 1 is coming here. So 1 1 will be 0. So Q1 will be 0. So S is equal to 0 and R is equal to 1, then output will be 1, 0. Q will be 1. Now, after that, if we take 1, 1, then what will happen? So, let us take here 1, 1. 1 and 1. So, what about again this situation? So, we have to look into what is the other input of this NAND gate 1. So, you can see from here, the earlier output was 0 here. So, 0, 1 gets output 1. So, this will be 1 only, from 1 to 1 only, no change. And this 1 is coming here. So, 1, 1 will be 0. So, earlier it was 0, now also it will be 0. So, Q bar is 0, Q is 1. So, again we can see there, if input is 1, 1, then there is no change in the output. Whatever output was previous phase, that will be remain like that. So, this is the truth table of SR. Now, you will see in 2-bit number, states are like that 0, 0, 0, 1, 1, 0, 1, 1. 4 states. So we can see what we have already covered here. 1, 0 we have covered here. 0, 1 we have covered here, except this 0, 0. So all 3 states we have covered. What shall be the output? If we put 0 here, say 0, 0. So that state is not defined. We put here don't care condition. Why? Because we see here, suppose this is 0 and this is 0. So both NAND gate was to make output logic 1, here 1, here 1, which is contradictory as far as logic is concerned, because this should be Q and this should be Q bar. Okay, if it is 1, it has to be 0. If it is 0, then it has to be 1, and vice versa. Both cannot be 1. However, these logics are telling that 0, 0 means it should be 1, 1. So that is why it is not defined. That is why we put this cross for 0, 0 state. Okay. Why? So if 0, 0 both was to be logic 1, but actually what happened? Since this, although theoretically we are taking these two NAND gates as identical, 1 and 2 NAND gate, but in practice, this may not be identical. Why? Because the change in the states occurs because of the conduction, and conduction takes place because of the electrons flow and doping, etc. So even one electron more in the device gets faster than the others. So suppose here NAND gate number 2 is faster than the NAND gate number 1. Faster means giving the response. If both inputs are 0, 0, and since NAND gate number 2 is faster than the NAND gate number 1, even say from 1 microsecond, it will give logic 1, and then once it is giving logic 1, it will compare to another logic gate, that is NAND gate number 1, to go to 0. It will force instead of 1. So in this way, it is uncertain. We do not know which one is the faster, although theoretically both are identical and having same response, but practically it is not possible. So that is why we put here don't care. So for this small class, up to that one, you will meet soon next video. Thank you so much for attending.